Electrolysis, running a galvanic cell backwards by running an electric current through the cell to produce the chemical change. Basically you're using electrical energy to make chemical changes, okay? And this is going to give you, this kind of cell is set up to be non-spontaneous to begin with. It's not thermodynamically favored, and it's going to have a negative E cell to begin with. By powering it though, you are able to, when you power it, you are able to get the reaction still to run. And it has a couple of different uses, okay, than just regular galvanic cell where it generates the power that we use for lots of different things, and it is spontaneous. So here, the thing to remember, and they always love to ask about this stuff too, the power supply. For an electrolytic cell, you figure out the E cell, and the E cell is going to be a negative value because it's non-spontaneous, and we know negative E cells are non-spontaneous. However, your voltage on your power supply has to be just slightly larger than the magnitude number in the negative E cell. So, for example, if we have a negative E cell for an electrolytic cell at negative 2.5 volts, your battery needs to be just above 2.5 volts. So 2.6 would do it, and now the reaction would run. But if they gave you like a 1.5 volt battery, wouldn't work. It has to be over the negative E cell number, this numerical value, in order to run the cell. And they do. This one I've seen multiple times in the last like 5 years. This one seems to be on there quite frequently. So they'll give you an example of, if we powered it with using this particular voltage, would it work? And then you would have to look at the negative E cell. If the voltage magnitude number is larger than the E cell magnitude, it will run, okay? All right, so here looking at the galvanic cell, the anode, of course, is going to be where oxidation occurs. The cathode is where reduction occurs. But you notice here, the electrons are flowing from anode to cathode, and it generates 1.10 volts here, okay? This is spontaneous, delta G is negative, it's thermodynamically favored. But if we reverse them, okay? If you reverse them now and you make zinc the reduction reaction in the cathode, cathode's still reduction though, but you're just making the zinc reaction now, the reduction, and you're making the copper one now, the oxidation. Now your E cell is really negative volts, so you have to power it with something that's greater than that 1.10 volts in order to get the electrons to flow. They're still going to flow from anode to cathode. It's just reversed now. Okay, just reversed. That's the same idea there. It's going to go that direction. Now, what is the purpose of electrolysis? Why do we use this? Why are we bothering to use energy? Well, a bunch of different industrial processes you can use electrolysis for. Electroplating, depositing thin layers of one metal onto another. Definitely for making, things that are aesthetically beautiful, where like they plate jewelry and utensils and things like that. But also they can plate a different metal on top that is not as reactive or corrosive, won't corrode as easily or rust on top of the other one so that it will last longer. So there is some purpose to, the process of electrolysis. Also, it can be used to isolate certain elements that don't really exist in nature by themselves. That's another reason for doing electrolysis. There's actually two different methods of way of using electrolysis. This particular diagram, as you can see, they have a silver anode, this electrode over here, and they have the solution with the silver nitrate in it. And as the electrons run, it adds the silver atoms to the spoon, so it electroplates the spoon over here. Okay, that would be an example of, beautifying something. Here though, okay, ionic compounds can be in molten state or they can be in aqueous state. But like for example here, they took some sodium chloride, and melted it down. So when we say melted ionic compounds, we're talking molten because it is really hot. It's like lava. Because remember, ionic compounds have really high melting points. So what you should realize too though here is you can't get alkali metals like out there in a mine or and actually find it in mineral deposits because it's not by itself. It's always in a compound. Alkali metals are so reactive they don't really exist by themselves. So if you wanted to isolate some sodium or potassium or these other things by themselves, you would probably need to do a process like this. And basically what happens is they attach it to the battery, and basically what they're doing here is getting solid sodium out of the process, and then chlorine gas is the other product. You can see the bubbles on that side. So if you do electrolysis with sodium chloride, you can't isolate the sodium. And then of course, if you isolate the sodium, you have to like submerge it in oil, because then if you leave it out in air, it's going to just start reacting with oxygen and other things in air. So like I said, alkali metals are so reactive, they don't really exist by themselves. And that is one of those processes there. Melt it down definitely will work. The other way that electrolysis works is an aqueous solution. That means it's dissolved in water. But that adds a little wrinkle to the process, because if you have it dissolved in water, water is present. Water can also be oxidized and water can also be reduced. Water is sort of a competitor here, okay? So water can be reduced instead of the metal ion at the cathode. And when water reduces, it has a negative 0.83 voltage, okay? And as you can see in this process too, it produces hydrogen gas and hydroxide. So reducing water makes it a little bit basic because you get the hydroxide out of it, okay? However, water can also be oxidized. So this oxygen reaction here, this is the reduction of oxygen, but if you reverse it, flip it, then you're oxidizing water here, okay? So flipping it makes it oxidize the water, and you end up getting hydrogen out of it as a product. So when you oxidize water, it actually makes it more acidic, as you can see, because you're producing H+ ions as a product. But if you flip it, just remember to change the sign, that. And now that when you're doing electrolysis in water, you have to watch and make sure that the water doesn't outcompete the substances you actually want oxidized and reduced. Okay? So, for example here, before we get to that, for the example, in aqueous solution of an ionic compound, the half reaction with the greater or more positive reduction potential is going to be reduced. Right? The greater or the more positive, it's going to be reduced. Now for the example here. If we're looking at this particular example, electrolysis of aqueous cobalt to bromide. Okay? What we have for cobalt to bromide in solution, you basically have cobalt, you have bromide, and you have water all in solution. The cobalt and the water, though, have the ability to be reduced as by their reduction potentials up here. Their half reactions and their potentials. Now, if we're looking at both of these, out of these two, which one has the more positive reduction potential? The cobalt does. So the species that's actually going to be reduced out of those two is going to be the cobalt. Okay, cobalt will be reduced instead of water, and for that particular instance, and that's because it has a more positive reduction potential. E red over there. But if we looked at something like this, barium bromide, Now, barium can be reduced and water can be reduced under these circumstances. But if you look over here at the reduction potential for reducing barium, it's negative 2.9 volts. And water is only negative 0.83. Out of these two, which one is more positive? The water one's more positive, so in this particular case, water is going to be reduced. So if you're trying to get barium out of this reaction, it's not going to work. If the intention is to get barium, that particular setup is not going to work. So you have to figure out a different way to isolate the barium. Okay, you go with the more positive reduction, and that's going to be the one that actually takes place at the cathode, the electrode on the reduction side. Now, you can think about the oxidation ones in two ways. The first way, which I don't think about it this way, but in aqueous solution of the ionic compound, the half reaction with the lower or more negative reduction potential will be oxidized. I don't like trying to look at the reduction potentials that way, so instead I just flip them and I make them oxidation potentials. When you flip them and make them oxidation potentials, you change the sign and then you just still go with the more positive one. Okay, flip them, change the sign, more positive is going to be the one oxidized. Okay, so for example here, if we're looking at the electrolysis of the cobalt bromide, in this particular case, we have the bromide and the water that can be, they're right here, they're going to be as products in the reduction potentials. But if you flip the reduction potentials, right, if I flip this, this becomes bromide, gives you bromine plus 2 electrons, and this becomes E-ox, which is negative 0.07 volts, right? And if I flip this bottom one, the water over here, we get oxygen plus the 4 electrons plus the hydrogens. And this becomes E-ox, which is negative 1.23 volts. So out of these two E-oxes, which one is the more positive value? The bromide. So at this particular case, bromide is going to be the one that's oxidized. Okay, bromide will be oxidized rather than the water in this particular case, because the flipping them, this is negative 1.07 versus negative 1.23. This is a more positive amount, so therefore that's the one that's going to be oxidized. Yes?
For reduction and oxidization, is it the one that's always more positive that's always
So when you flip them for oxidation, look for the more positive, and for the reduction ones, you don't have to do anything, you just look for the one that's more positive.
Okay.
But when you flip them, don't forget to change the sign. Last but not least, this last example here, we have electrolysis of cobalt 2 fluoride. This particular case, you would flip this one. Okay, so we have the 2 fluorides going to F2 plus the 2 electrons, and this becomes E-ox, but it's now negative. And like I said, you flip this one, you get the 2 waters going to the oxygen plus the 4 electrons, and this turns into E-ox, which is negative. Out of those two in that particular case, which one's going to be oxidized? Yes, the one that's more positive is going to be this one, which is the H2O. So if you were trying to isolate the fluorine, well, you're not going to be able to do it with that particular reaction. Okay, so water would be oxidized instead of the fluoride here, so you wouldn't get the fluorine as a product. Instead, you were going to get a bunch of H pluses, and it's going to turn acidic because you have a lot of H pluses here. That's going to be part of your product. Okay.